When it goes down straight, it's gonna protect it. If the plant or something goes down straight, it's
Okay, class. So please collect your class lecture for today from the front row. And so as I said, your homework 4, which will be due Monday, 5 p.m. and your quiz 5, which will be due Monday before class. But as I said, the quiz is it's open book, so you can read the book and then just answer the questions. Okay. Okay, now start working on the very last part of our manometer class example. Class example 7D. Have we started working on that? I think we just stopped at the end of
the D.
Yeah.
We stopped.
Okay, so those who are in Zoom, can you see the screen?
Well, I'm gonna say this. I have to say.
Okay, so let's start working on that. Can anyone read the class example 7 loudly? And okay, thank you very much. So for this question, the very first thing I think, since you have the black and white copy, most probably you can't see the interface clearly. So in between C and D, there is a different fluid here. Okay, different fluid here. So we have two interface C and D. So from the given values here, okay, for this question, one special thing is we know a pressure like between one, like in between 1 point, which is not atmospheric pressure, which is good, and that will help us to solve this question properly. Like we don't know the pressure at A, we don't know the pressure at B, but we know pressure at 1 point. So that will actually help us, so that will reduce some calculation. So we don't need to move from point A to B. We can start from A and we can stop at point D because we know the pressure at D. Okay. So let's write down what are the given values and then what we need to find out. Okay. So help me to write down the given values. What is the very first value we know?
Pressure at D is 2 kilopascal.
Pressure at D is 2000 or 2 kilopascal or 2000 pascal. Okay. So PD is okay. So what else we know? What else we know? Okay. So we know the density of all the fluids, right? So density of AC equals to density of dV equals to 800 kg per meter cube, and density of CD equals to 1000 kg per meter cube. Okay. Okay. And what we need to find out? PA and PB. Okay. Now, if you look at the question here, PA and PB, they are not dependent on each other, at least for calculation wise, only because we know the pressure at D. So you can calculate PA first, then PB, or PB first, then PA. It will not make any problem because we know the pressure at D. Okay. So let's start working on that. I will work with PB first, and I will let you work on PA. Okay. So for PB and PA. Okay. So for PB, if I start from this point, what is the pressure at PB? I don't know. That's what I need to find. So I will just write down PB. Now, where is the next interface? From B, where is the next interface? Where is the next interface? D, yes. And D is actually above or below the point B? Above, so we need to subtract, and we need to subtract the pressure for this amount of fluid, right? Which is gamma BD, and what is the distance? 250 over 1000. Now, once we are here, do we know the pressure at this point? That is actually PD, right? Okay. Now let's write down what values we already know and then do the calculation.
Is that 1,000 just for like converting from millimeters to?
Yes, yes, yes.
Can we just write like 0.25 down?
You can, yes. So PD is what? 2000. And do we know the gamma BD?
We can find it.
We can find that, yes. So we know the density. We can find that because gamma equals to gamma times, sorry, rho times gravity, yes. So the rho is for BD 800 multiplied with 9.81. So give me the answer for
784.
what will be the answer for PB?
260.
21?
Yeah.
Say it again, 21?
Oh, wait. Yes.
3,960.
2,962.
Okay. Anyone else? 3,962 Pascal, but they are asking you to find the pressure in kilopascal. So you will divide that by 1,000 and the answer will be 3.96 Pascal. Okay. Now it's your turn, work on PA. Okay. You have 2 minutes. Then I will check with you what with PA. So start with PA, find the next interface. How many interfaces you will have if you start from A and you stop at D?
2.
2, C and D. And both of them are above like previous point. So that means you will subtract that pressure from PA. To start working on that, and if you have any confusion or anything, let me know. I just try to work on that.
No proof. Yeah. True. True. God, how many minutes?
I don't know. You did
Yeah, that's why you got not changed the current is that.
50,000
now. Oh, you remember about 9.81, right?
I got 10,792.
That's the
You right? There, the road. The road. Which is this? 11.
No, we already had that. Oh.
There's two different densities. This is different. From C to D, it's different density than this one and this one. You just do it. No.
But these options definitely my favorite.
Yeah, I did. Oh, this is 11. Not boom. Then boom.
Then yeah.
Wow.
Why'd you convert it to all the other stuff? Wait,
You already, you can.
Yes, now you're at that point, but we have one more layer of fluid. That's right. Yes.
Yeah.
You have an answer?
2,936.
You got 2,900. You got 20,000. Check the calculation again. Okay.
Yes.
Okay. So, you have an answer? 1.9. Let's check what is it. What is 1,003? 30,000. That was 1,003. Just check that calculation again. And this one is 800. That is the density. Calculate the specific weight. Multiply that. Yeah, so do that calculation. Okay. So it seems almost all of you got the answer. So let's do it together. So if I start from PA, where is the next interface? If I start from A, C, which is above point A, right? So I will add this amount of fluid here, which is 30/1000. And what is the density of that fluid? This one is gamma AC, which is 800. So 800 multiplied with 9.81, right? And from C, where is the next interface?
D.
D. And at D, again, it's above point C, so it will be 65/1000. And what is the okay, equals to PD, right? And we know PD is what? 2000, okay? Now give me the answer for PA in Pascal and kilopascal. What is the answer you got?
2,936.
2,936 Pascal, but we need to convert that into kilopascal, so it will be
33 pascals.
okay. So we have the value for PA and PB. If the point B pressure was not known, we had to go from A to B, and still we couldn't find the pressure because we didn't know the pressure at A and B, right? So now, if I ask you any question in your test or in your homework where you know the pressure at some point in between the first end and the last end, you can take advantage of that part, right? For the given values, like you know how to use that one, right? Okay, good. Now, till now, we only calculated all the pressure variation and everything. Now, the next part of this course, we will try to find how can we find the hydrostatic force. Okay, what is the relation between pressure and force? Can you remind me that? What is the relation between pressure and force? So pressure equals to force over area. Is there anything I need to mention here, like the direction of force on the area or something? Like F should be perpendicular to the area, otherwise it will be just the shear stress, right? Okay, so we know the pressure. Now we will try to find out how can we find the hydrostatic force. Okay. Now this hydrostatic force, it can be on any type of surface. So I just chose few examples here. The very first one is what? This one? A swimming pool here, right? Now the wall of the swimming pool for this picture, do you think that is vertical or it is kind of inclined? This one is vertical, just straight vertical wall here. Okay. For swimming pool, it can be carved, I know, but I just chose the simplest one where the wall is the vertical one, right? What about this one? This is a picture of what? Hoover Dam, right? So for Hoover Dam, the wall, like this wall here, this one is little bit inclined, like this way. Okay, it's not straight, little bit inclined, and all the water is creating some sort of pressure. Again, here, all the water here, they are creating some sort of pressure here, right? Now, this one is just a straight vertical wall or plate. This one is what? Inclined, right? Inclined surface or plate or plane. Now, what about this one?
Which one? Oh, curve.
This one is a curved one. This is a picture from Atlanta Aquarium. Have you ever been there? It's a huge facility and it's so interesting. So there is a one part just like that where you can walk, and on top of your head there will be like this structure. Inside that there are like hundreds of different types of fishes there. Wow. And you can
That's cool.
that's really cool, and they have a great dolphin show. So for this one, you can imagine like the huge amount of pressure is coming from the water here, right? So what will happen if you can't design properly, it will break down on your head, and obviously you will not survive. So it's very important to know what amount of pressure or force is coming and how you can calculate that, right? So this one is the curved surface. What about this one? This is a tank which is carrying some sort of fuel or oil, something like that. Again, what type of surface is that? It's a circular one or a straight or inclined? It's kind of circular or maybe curved, right? That means we can have vertical surface, we can have inclined surface, and we can have what? Other than vertical and inclined, what can we have? Curved surface, yes. So that's what we will try to learn. How can we calculate force on these different type of surfaces? Okay. So let's do a very quick overview for the pressure. Do you remember what is the pressure variation in horizontal direction? dP over dx is what? It's 0. There is no pressure variation. And you can see that from this plate, if that is the horizontal plate, at any point, the pressure will be 0. Now, for the vertical direction, we know there was a pressure variation, right? That depends on the type of the fluid we are using and the height of that fluid column, right? And for this one, we can have two different type of things. One is incompressible one, and one is the compressible one. So this one is liquid and this one is gas, right? For incompressible one, we had P equals to gamma Z or gamma H, basically gamma times depth, right? And for the compressible one, we had a little bit complex equation. It was P equals to P naught e to the power G RT. Like you have that expression. If you can't write that right now, that's okay because you have that from your previous classes. So we know in vertical direction the pressure will be different at different points, right? So for next few classes, that's what we will try to learn. How can we find a combined force or resultant force for this pressure distribution? And we will use your statics class and your favorite integration a lot in this part. So we will do some review about those parts. Okay. Do you remember uniformly distributed load, triangular load, and how can you find the resultant force and everything? Good, very good. We have to use that part. Okay. Now, just for this one, before we start working on that, I want to show you one demonstration. Hopefully that will help you to understand the pressure better. So I will share the screen, this camera. Okay. So all of you can see that here, right? Like there is a stack of books here. So what we will do, we will consider two books as one fluid particle. Okay.
Is your hand supposed to like show up on there?
Okay.
Like you couldn't see your
see it.
hand like on the screen.
Oh, I think it's just every time it creates some sort of problem. Most probably, since I'm sharing this one, that's why nothing is happening there. Yes. No. Okay, what I will do, I will just stop share this one. I will just show you what is happening here. Okay. So it will be not on the video, but that's okay. Okay, now you can see that, right? Okay, so here we will consider two books as one fluid particle here. So how many fluid particles we have here? 3, because two books will be one fluid particle. So we have 3 fluid particles here, right? Now, on top of the very first fluid particle, it's open to atmosphere, right? What is the pressure here? It's open to atmosphere. That is the absolute pressure, 101 kilopascal. But if I ask about the gauge pressure, that is 0 here, right? Now, on top of, just below the first fluid particle, what is the pressure here? The pressure due to this fluid particle, right? What about the pressure at this point? Pressure due to this one and this one, right? So if I try to visualize a little bit better, so this time I have pressure due to this one and this one, which is a little bit better, like higher than the first one, right? What about at the very end? How many fluid particles we have here? 3. So the pressure will be 3 times of the first one, right? So how about I add this one? So at this point, we have pressure due to this particle. At this point, we have pressure due to this one and this one. That's why we got extra pressure here. At this point, we have pressure due to this one, and this one. So we have a huge pressure here, right? Like this one, this one, this one. And if you visualize that, do you think you will get something like that pressure distribution? At top, it's 0. Here, it's just the pressure due to this particle. Here, it's due to these 2 particles. And at the end, is the pressure due to 1, 2, 3 particles, right? So it's kind of like that in fluid also. You can, if you draw that, it will be kind of same. So let's again explain this one here. Those who are in Zoom, can you see the screen right now? Okay. So just for this one here, at the pressure, what is the pressure here? It's open to atmosphere, 0. If I think this one is 1 meter, this one is 1 meter, and this one is 1 meter, what is the pressure here? 0 plus gamma multiplied with 1. So the assumption, we are working with incompressible fluid, okay? So P equals to gamma times Z. And Z scale is going this way. Okay. Now, what is the pressure here? 0 times gamma multiplied with 1. And what is the additional pressure here? Pressure due to that amount of fluid, right? What about here? We have 0 times, and if the pressure for this one, oops, we have 1 extra pressure there. So finally, what do we have here? 0 plus how many pressure for this one? 3 gamma, right? What about this one? 0 plus 2 gamma. Here, just gamma, and here it's 0. So if you draw that, or if you find out the value, what will be the pressure profile here? What will be the pressure profile? try to draw that one on both sides here, okay? At the same time, give me the pressure profile, what will be at the bottom, okay? Just one hint. This is a horizontal surface, so pressure variation should be what? Horizontal surface, pressure variation is zero, right? There is no pressure variation. That means there will be same pressure at every point. So try to draw something for this one. What will be the shape and what will be the pressure distribution here? Okay. If it's wrong, I don't care. Just try to do something, and I'll be here just to help you. Okay. Draw something on these two pictures. What do you think? What will be the pressure profile in these two plates? One vertical plate and one horizontal plate. For the vertical one, you already know the value, so you can calculate that and decide for that. That will give you the answer. For the horizontal one, pressure should be same. To have same pressure or same magnitude at every point. What type of distribution is that on your settings? To have the same magnitude of force or pressure at every point. Distributed, what type of distribution? Uniformly distributed. Can you draw the uniformly distributed pressure on the right one? Yes. Since there is no variation in pressure in the horizontal direction,
So,
yeah. What does it mean?
this.
Yes, that's the thing I want for this one. Just draw something and
What? Hopefully.
study that for the chest. So just find the value and use the one. So profile. If you find something, okay, here you will have this one. This, right? So just move the whole thing here. And draw the profile for this one. Okay. Do you know how to draw a uniform? Let's go on. So the same thing here. Exactly same thing. You have two bubbles here. You have one plate or something. Don't use it here. That will give you that. Okay. For this one, when you are trying to find on the tank ends, if you look at the arrow you did, you are actually implying all the forces is on this plate, right? But that's not the tank. That is tank bottom here, which you did here. This time I want to know what will be the force profile on this wall, not on the bottom. Okay, so you have the shape, but you have the wrong arrow sign here. Okay, so it seems most of you got the idea. Some of you are still lost. So let's go through here. So for the bottom, if I think that this is the same swimming pool, 3 meter, that will be a very deep swimming pool. I should have used 3 feet. So 3 meter will be kind of 10 feet swimming pool. Which is pretty unusual for a house, I guess. So if I use 3 meter here, what is the pressure here? 3 gamma, right? And at any point, the pressure will be 3 gamma because it's the horizontal plate. So the pressure distribution will be just this. Okay. And every time the magnitude of the pressure will be what? 3 gamma, right? Now, what about this one? You have 0 here. At 1, you have gamma. At 2, you have 2 gamma. At 3, you have 3 gamma. So what will be the pressure? What shape it should be? A triangular. Okay. And the direction should be this side, this side, this side, because all the water is actually creating the pressure on the wall, right? The same thing on this side also. Here, here, and here. Okay. Now, in real, just below the swimming pool water, obviously you have brown, but I just made a little bit simplification here. I kind of used that as a tank. So below the tank, again, you have air. So what will be the pressure? Atmospheric here. But on top of this plate, the pressure is 3 gamma here. Now, one tricky question I can ask you for your test or something. Do you think this pressure distribution will be always triangular, like for the vertical plate?
No.
When it can be different? Yes. So there can be 2 types of answer. The first answer can be if we don't use the straight plate, if it's curved surface, obviously the pressure variation will be different. We will discuss that. But just for the vertical plate, the pressure can be different if you use compressible gas. What is the pressure variation here? You see, you have a pressure here, temperature here, ideal gas law, and the distance and everything. So one good point to be noted will be, just write down that for compressible gas or compressible fluid, you can have different type of pressure profile because temperature will play a role there. Okay. Here we don't have any variable except gamma. And gamma doesn't change with temperature for incompressible fluid. That's what we did here. But for the compressible fluid, we can have different type of pressure profile. Okay. So I will stop here for today. From Monday, we will start again and we will try to see if we can get idea what will be the pressure profile for curved surface and inclined surface and everything. Okay. You all have a good weekend and I will see you on Monday.